Welcome to this walkthrough of problem number 2132, stamping the grid. In this video, we'll break down the problem, explore different approaches, and guide you through an effective solution. Let's dive in. In this problem, you are working with two binary matrices, a grid and a stamp. The grid is an MXN matrix where each cell is either 0, representing an empty space, or 1, representing an occupied space. The stamp is an HXW matrix, and its cells are also binary, with 1 indicating a part of the stamp and 0 meaning no stamp. The challenge is to determine if it is possible to use the stamp to cover all the 0s in the grid. To do this, everyone in the stamp must align exactly with a 0 in the grid, and the stamp cannot overlap any 1s in the grid. It is worth noting that a single 0 in the grid can be stamped multiple times, but the 1s in the grid must remain untouched. Now, let's explore an example to clarify the task. Consider a grid where most of the cells are 0s, except for a few 1s, and a stamp matrix that is a diagonal pattern of 1s. In this case, the output is true, because the stamp can be rotated or flipped as needed to match and cover all the 0s in the grid. Since the grid's 1s are not disturbed in the process, the stamping is deemed successful. This example illustrates the flexibility provided by rotating and flipping the stamp, which can help in aligning it with the available empty spaces. However, not all configurations will allow for successful stamping. For instance, if the grid has 0s that are scattered in such a way that they can't all be covered by the given stamp while avoiding the 1s, the output will be false. In the second example, the grid and stamp are such that the stamp cannot be rotated or flipped in any way to cover all 0s without overlapping or touching the 1s. This highlights the importance of carefully analyzing the placement of both the 0s and 1s in the grid to determine whether stamping is feasible under the given constraints. To begin, let's consider the brute force approach. The intuition here is straightforward. We attempt to place the given stamp matrix, which is of size h by w, at every possible position in the m by n grid. For each position, we check if the stamp fits entirely within the grid, and more importantly, if all the ones in the stamp align perfectly with the ones in the grid at that location. If these conditions are met, the stamp is deemed successfully placed. The steps are as follows. First, we iterate through all the positions where the top left corner of the stamp can fit within the grid. Then, for each of these positions, we compare the corresponding subgrid of size h by w with the stamp matrix to verify alignment. Finally, we keep track of the regions where the stamp was successfully placed. However, this approach has a significant drawback. Its time complexity is m multiplied by n multiplied by h multiplied by w, as we need to evaluate all possible placements and perform comparisons for each. While simple to implement, this approach becomes computationally expensive as the grid and stamp sizes increase, making it impractical for larger inputs. Now, to address the inefficiency of the brute force method, we turn to an optimized approach using prefix sums. The key insight here is that verifying whether all the ones in the stamp align with ones in the grid can be reduced to a subgrid sum check. Specifically, if the sum of the elements in the h by w subgrid matches the total number of ones in the stamp, then the stamp placement is valid. This eliminates the need for cell-by-cell comparisons. The process begins with computing the prefix sums for the grid, which allows us to query the sum of any subgrid in constant time. Once this pre-processing is complete, we iterate through all possible placements of the stamp. For each placement, we use the prefix sum array to efficiently compute the sum of the corresponding subgrid and check if it matches the required value. This method drastically reduces the overall time complexity to m multiplied by n, as the prefix sums are computed once, and the placement verification for all positions is linear in complexity. While it introduces a pre-processing step, the reduction in runtime makes this approach highly scalable for large grids and stamps. Another approach to solve this problem is greedy reverse simulation. Instead of directly placing stamps onto the grid, we start with the assumption that the grid is fully covered by stamps. From there, we iteratively remove stamps while ensuring that the configuration remains valid and matches the constraints of the input grid. Here's how it works. We begin with the grid completely stamped, assuming every position is covered. Then, we identify and remove stamps from positions where the constraints of the grid are satisfied. The goal is to ensure that after removing the stamps, the remaining configuration aligns perfectly with the original grid. The complexity of this method depends on the number of valid stamp positions, but it is typically more efficient than brute force. However, this approach comes with its own trade-offs. It can be less intuitive to understand and significantly harder to implement correctly. Despite its potential efficiency, the complexity of maintaining a valid configuration during the removal process and debugging makes it less appealing in practice. After evaluating all the approaches, the optimized prefix sum method emerges as the most efficient and practical solution. It strikes the right balance between simplicity and computational efficiency. Unlike brute force, it avoids redundant calculations by leveraging pre-computed prefix sums, and compared to reverse simulation, it is much more straightforward to implement and debug. The key insight that makes this approach so powerful is recognizing that verifying a stamp placement can be reduced to checking subgrid sums, which the prefix sum array allows us to compute in constant time. This realization eliminates the need for intensive cell-by-cell comparisons, drastically cutting down the computational overhead. While the prefix sum approach introduces some upfront cost for preprocessing, this cost is negligible compared to the performance gains during the verification process, especially for larger grids and stamps. Furthermore, it is robust and generalizable, making it less error-prone and easier to adapt to edge cases. Overall, the prefix sum method provides an elegant and scalable solution to the problem, making it the optimal choice for this scenario. This problem involves determining where a rectangular stamp of size hxw can be placed on a binary grid of size mxn. The key condition is that all 1s in the stamp must align with 1s in the corresponding cells of the grid. We start by validating the input dimensions to ensure the grid and stamp sizes are compatible, and that the constraints 1 equals h equals m and 1 equals w equals n are satisfied. If these checks pass, we proceed to initialize a result matrix, which will store whether the stamp can be placed at each valid position in the grid. To assist in this process, we define a helper function that determines if the stamp fits at a given position, I, j. The algorithm then uses a sliding window approach to iterate through all possible top-left positions of the stamp in the grid, extracting the corresponding submatrices to check for valid placement. The goal is to systematically identify which positions can accommodate the stamp while maintaining alignment of 1s between the grid and the stamp. To determine if the stamp fits at a specific position, we compare each cell in the hxw submatrix of the grid to the corresponding cell in the stamp. If the stamp contains a 1 at a particular cell, the corresponding cell in the grid must also be 1. If even a single mismatch is found, we mark the position as invalid in the result matrix. Otherwise, if all cells align correctly, we mark it as valid. Checking submatrices directly can be computationally expensive, especially for large grids and stamps, so we optimize this process using a prefix sum matrix. By pre-processing the grid into a prefix sum matrix, we can quickly calculate the sum of any submatrix in constant time, which allows us to efficiently verify whether all cells in the submatrix are 1. This optimization significantly reduces the time complexity, making the algorithm more scalable for larger inputs. Once the placement checks are complete, the result matrix provides a clear picture of where the stamp can fit. Using the prefix sum matrix not only accelerates the stamp placement checks but also eliminates redundant calculations for overlapping regions of the grid. This optimization transforms what would otherwise be a brute force approach into a more efficient solution. The algorithm also incorporates considerations for edge cases, such as when the stamp dimensions match the grid dimensions exactly, or when the grid contains only 0s or 1s. Another edge case to handle is when the stamp consists entirely of 1s or entirely of 0s, as this affects placement logic. To implement the solution, we rely on key data structures, the grid matrix to represent the binary input, the prefix sum matrix for efficient submatrix queries, and the result matrix to store valid placement results. From a complexity perspective, the brute force approach has a time complexity of O, M H plus 1, and W plus 1, asterisk H asterisk W, while the optimized approach reduces this to O, M asterisk N, for prefix sum computation and O, M H plus 1, and W plus 1, for placement checks. The space complexity increases slightly with the use of the prefix sum matrix, but this is a worthwhile trade-off for the improved efficiency. Consider an example where the grid is a 3x4 matrix, and the stamp is a 2x2 matrix. The grid contains a mix of 1s and 0s, while the stamp is filled entirely with 1s. First, we compute the prefix sum matrix for the grid, which allows us to summarize the values of any submatrix efficiently. Next, we evaluate each potential top left position, I, J, for placing the stamp by checking if all cells in the corresponding 2x2 submatrix of the grid align with the stamp. After processing all positions, the result matrix is produced, indicating where the stamp can fit. In this example, the result matrix shows valid placements only at the top left corner of the grid, with the rest of the positions marked invalid due to mismatches. This step-by-step approach ensures that the algorithm is both accurate and efficient, even for larger grids and stamps. To solve the problem, we start by importing the DEEC module and defining our solution class. The main function here is possible-to-stamp, which determines if all zeros in the grid can be covered by stamps of a given height and width. First, we calculate the dimensions of the grid using len, grid, for rows and len, grid, 0, for columns. We initialize two matrices, diff, which is used to track the difference values for marking valid stamp placements, and stampable, which helps identify the top left corners where a stamp can be placed. Next, we pre-compute which cells in the grid are stampable. This is done by iterating through all possible top left positions of the stamp and checking if all cells in the corresponding region are zeros. If they are, we mark the top left corner in the stampable matrix with a value of 1. After this, we move on to marking the differences for valid stamp placements. For each stampable position, we update the diff matrix to reflect the boundaries of the stamp's coverage. This involves incrementing the starting point and decrementing the adjacent boundaries to prepare for efficient propagation later. Then, to propagate these differences across the grid row by row, we iterate through the matrix and update the values in the diff array cumulatively, which helps us calculate the final coverage efficiently. After propagating differences row by row, we do the same column by column to ensure that the entire grid is covered with the cumulative values in the diff matrix. Once this propagation is complete, we check if all zeros in the grid are covered by stamps. This is done by iterating through each cell in the grid. If a cell contains a 0 and the corresponding value in the diff matrix is less than or equal to 0, that means the cell is not covered by any stamp, and we return false. If we successfully iterate through the entire grid without finding any uncovered zeros, we return true, indicating that it is indeed possible to cover all zeros in the grid with the given stamp dimensions. This approach ensures the solution is both efficient and easy to understand by leveraging the diff matrix to handle stamp coverage calculations in a streamlined manner. Here, we begin by defining the core structure of our solution. First, we import the necessary packages and declare the solution class. The method possible-to-stamp takes the grid, as well as the dimensions of the stamp, stamp height and stamp width, as parameters. To start, we calculate the grid dimensions, m and n, and initialize two matrices, diff, which will be used later for marking stamp placements, and stampable, which identifies the cells where a stamp can fit. Next, we iterate through each potential top left corner of a stampable area. For each position, we use nested loops to check whether a stamp of the given dimensions can fit without overlapping any one cells in the grid. If all cells within the dimensions of the stamp are 0, we mark the current position in the stampable matrix with a value of 1, indicating that a stamp can be placed here. This forms the foundation for determining valid stamp placements. Now that we have identified the stampable cells, we use this information to update the diff matrix. For every valid stampable position, we adjust the diff array to efficiently mark the area covered by the stamp. This is done by incrementing the top left corner of the stamp and decrementing the boundaries just outside the stamp's range. This approach, known as a difference array technique, allows us to propagate the stamp effects efficiently in subsequent steps. After marking the differences, we propagate the values in the diff array. First, we process each column to accumulate the vertical effects, ensuring that the stamp influence extends downward. Then, we handle the rows to account for horizontal propagation. By the end of this step, the diff array reflects the cumulative effect of all valid stamp placements, making it easier to verify the grid coverage. Finally, we verify whether all 0 cells in the grid are covered by the stamps. For each cell in the grid, if the cell contains a 0 and the corresponding value in the diff matrix is less than or equal to 0, it means that this 0 cell is not covered by any stamp. In such a case, we immediately return false, indicating that it is not possible to stamp the grid as required. If we successfully iterate through the entire grid without encountering any uncovered 0 cells, we return true, confirming that the grid can be completely stamped. This marks the completion of our solution, where we use efficient algorithms to check stamp placements and verify coverage with minimal computational overhead. In this example, we are working with a simple 3x3 grid and a stamp of size 2x2. The first step is to initialize the problem settings. We determine the grid dimensions, which are 3 rows and 3 columns, and set up 2 matrices, the diff matrix, which will help us track coverage adjustments, and the stampable matrix, which will indicate where stamps can be placed. Both are initially filled with zeros. Next, we pre-compute the stampable cells by iterating through possible top left corners of the stamp, checking if a stamp of size 2x2 can fit without overlapping A1. For the given grid, none of the subgrids, such as 0, 0, 0, 1, or 0, 0, 1, 0, are fully 0. As a result, no positions are valid for stamping, leaving the stampable matrix filled with zeros. Since no valid stamp placements were found in the previous step, the diff matrix remains unchanged and filled with zeros. The next step is to propagate the differences stored in the diff matrix by calculating cumulative sums along rows and columns. However, since the diff matrix contains only zeros, no changes occur during this propagation. Finally, we validate whether all zeros in the grid are covered by stamps. This involves checking each zero in the grid and confirming whether its corresponding cell in the diff matrix has a value greater than 0. In this case, the 0 at position 0, 0 is not covered, leading to a result of false for this grid configuration. Now, consider a fully stampable 2x2 grid. We start by initializing the grid dimensions and matrices as before. The diff matrix is a 3x3 matrix filled with zeros, and the stampable matrix is a 2x2 matrix initialized with zeros. During the pre-computation of stampable cells, we find that the subgrid 0, 0, 0, 0 is entirely zeros, allowing a stamp to be placed at position 0, 0. This updates the stampable matrix to indicate this valid placement. Next, we mark the differences in the diff matrix to account for this stamp. At the top left corner, 0, 0, we increment its value by 1 and adjust boundaries to subtract appropriately, resulting in a new diff matrix. After this, we propagate the differences row-wise and column-wise, computing cumulative sums to finalize the coverage. The updated diff matrix now reflects the full coverage of the grid. To validate the coverage for this fully stampable grid, we check that all zeros in the grid correspond to values greater than 0 in the diff matrix. Since this condition is met for every 0, we conclude that the grid is completely covered by the stamp placements. The result for this input is true. In contrast, for larger grids with partial coverage, the process would follow similar steps, but the final validation might fail if some zeros are left uncovered due to obstructive ones. For example, in a 3x3 grid with a central 1, partial stampability would lead to a result of false as not all zeros would be covered. This demonstrates how the algorithm adapts to different grid configurations and stamp sizes. We begin by analyzing the time complexity of the function possible to stamp. The first step is pre-computing the stampable matrix. Here, we iterate over all possible top left corners of the stamp in the grid using an outer double loop. For each position, I, j, we check if the stamp height x stamp width submatrix in the grid consists entirely of zeros. This requires iterating over all the cells within the submatrix, which takes O, h asterisk w, time per position, where h and w represent the stamp's height and width. Since the outer double loop iterates over h plus 1, asterisk, n w plus 1, possible positions, the total time complexity of this step becomes O, h plus 1, asterisk, n w plus 1, asterisk h asterisk w. Next, we consider marking differences in the diff matrix. Here, we iterate over the entire mxn grid. For each valid stampable position, we update the diff matrix, which involves making a constant number of updates specifically, 4 updates per position. As a result, this step contributes an additional O, m asterisk n, to the time complexity. The next step is propagating differences in the diff matrix using prefix sums. This involves 2 loops, one to propagate row-wise and another to propagate column-wise. Each of these loops iterates over all rows and columns, which means both the row-wise and column-wise propagation each take O, m asterisk n, time. Consequently, this step adds O, m asterisk n, to the overall time complexity. Following this, we verify the final coverage of zeros in the grid. This involves iterating over the entire grid to check whether all zeros are covered by the stamps. This operation also takes n time. When we sum up all these steps, the total time complexity is dominated by the pre-computation of the stampable matrix, which is h plus 1 n w plus 1 h w. In the worst case, particularly when the stamp dimensions are large, this simplifies further to n h w. Now, let's turn our attention to space complexity. The input grid, which is provided as part of the problem, has a size of mxn. In addition to this, we use a diff matrix of size m plus 1 h n plus 1 to track the differences for propagating prefix sums, which contributes m n to the space complexity. We also maintain a stampable matrix to store positions in the grid where the stamp can be placed. This matrix has the same dimensions as the grid, mxn, and thus also contributes m n to the space complexity. Finally, we use a few temporary variables, such as loop counters and other small constants, but these are negligible in comparison to the matrices. When we sum these contributions, the total space complexity of the algorithm is dominated by the diff and stampable matrices, resulting in m n. To understand the efficiency of our approach, let's compare it to a brute force solution. In a naive implementation, we would simulate stamping at every possible position in the grid. For each position, we would explicitly check whether the HXW submatrix is valid and then verify coverage for all zeros in the grid. This approach would require iterating through all HXW submatrices for each position in the MXN grid, leading to a time complexity of m n h w. Additionally, the coverage verification step would be far less efficient. Our optimized approach, on the other hand, uses a prefix sum technique with the diff matrix to reduce redundant computations. This allows constant time updates for each valid stampable position and ensures that coverage validation is linear in grid size, i.e., m n, after the pre-computation. As a result, the overall process is significantly more efficient than the brute force method. Finally, let's analyze the best, average, and worst-case scenarios for the algorithm. In the best case, the grid is filled entirely with ones, meaning no stamps are possible. Here, the algorithm terminates early after pre-computing the stampable matrix, resulting in a time complexity of m n. In the worst case, the grid is filled entirely with zeros. This requires checking every single cell for stamping, leading to the maximum time complexity of m n h w. The average case depends on the distribution of zeros in the grid and the dimensions of the stamp. However, since the nested loops for stampable computation dominate the runtime in most cases, the complexity tends to be closer to the worst case. From a mathematical perspective, the dominant term in the time complexity arises from the pre-computation step, where each position, j, is checked for a submatrix of size hxw. This results in m n h w in the worst case, as all other operations, difference marking, propagation, and final validation, are linear in grid size and do not surpass the pre-computation in asymptotic growth. When working on the stamping the grid problem, there are several common mistakes to watch out for. First, boundary checks are crucial. If you forget to ensure that the stamp fits entirely within the grid's dimensions, you could end up with out-of-bounds errors. Always verify that the bottom right corner of the stamp matrix stays within the bounds of the MXN grid. Another frequent issue is overlooking how overlapping stamps interact. Overlapping placements can create unexpected grid states, so your implementation should carefully handle overlaps, especially when verifying binary constraints. Inefficiencies can also arise when dealing with large grids. A naive brute force approach that iterates through all possible positions and orientations of the stamp can lead to excessive computations. To avoid this, consider optimization techniques like pre-computing reusable data structures, such as prefix sums, to minimize redundant checks. Additionally, some solutions fail because they skip validating whether the stamp only covers valid cells, like those marked as 1. Always ensure that the binary constraints are met for each position. Lastly, misinterpreting the problem requirements can cause solutions to fail edge cases. For example, you need to clarify whether the entire grid must be stamped or if leaving valid empty cells is allowed, as this affects how you approach the solution. Now, let's talk about some insights specifically related to interviews. One key area of focus is optimization. Interviewers often want to see if you can move beyond a basic brute force approach and implement more efficient solutions, such as using prefix sums or sliding window techniques. Make sure to highlight these optimization steps explicitly when explaining your solution. Another area to prepare for is edge case handling. Expect scenarios like single-cell grids, very large grids of dimensions up to 10*4x10*4, or cases where no valid stamp placements are possible. Demonstrating that your solution is robust and accounts for these edge cases can set you apart. Additionally, be ready to discuss trade-offs between time complexity and space complexity. For example, you might need to explain the balance between the time complexity of O, M*N*H*W, and the additional memory usage required for certain optimizations. Lastly, if you want to practice related problems, consider tackling LeetCode 221, which focuses on finding the maximal square, or problems like LeetCode 1277 and 85 that deal with counting submatrices and rectangles. LeetCode 304, which involves range sum queries in 2D, also shares some similar optimization concepts. Finally, let's explore some alternative approaches and the trade-offs associated with them. One effective technique is using a prefix sum matrix. By pre-processing the grid into a prefix sum structure, you can perform constant time region sum queries, significantly reducing the time complexity for validation. However, this approach comes with a trade-off: it increases space complexity due to the additional memory required for the prefix sum matrix. Another optimization strategy is the sliding window technique. This method reduces redundant checks by systematically sliding a fixed window, corresponding to the stamp size, across the grid. It's more memory efficient since it avoids creating large auxiliary data structures, but it may involve slightly more complex implementation logic. Finally, dynamic programming offers another alternative. By pre-computing valid placements and regions, you can make the solution more efficient. However, as with prefix sums, dynamic programming requires extra memory to maintain the DP states, which can become prohibitive for very large grids. Choosing the right approach involves weighing these trade-offs based on the constraints of the grid size and the resources available. That brings us to the end of this walkthrough for problem number 2132, stamping the grid. We hope you found this explanation helpful and gained valuable insights into solving grid-based problems. If you enjoyed this, don't forget to like, share, and subscribe for more tutorials. See you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!